So to this point, we've been doing regression analysis where we looked at what happens when we project some x on y and we're estimating this line y is equal to beta naught plus beta 1 x1. And we've plugged in our data to the ordinary least squares estimator. We've gotten our estimate of beta 1 is 10.23. Our estimate of beta naught is 31.82. From there, we found all of our sums of squares. And now we have a few things left to do. We need to find our r squared, our adjusted r squared. We want to find the standard errors of beta 1, do hypothesis testing, and then build some confidence intervals. R squared is just the sums of squares from regression divided by the total sum of squares. We have both of these numbers from before. This is 115.0.64 over 1718.75, and this gives us approximately 0.6695. R squared is relatively straightforward. The adjusted R squared is a bit more complex. This adjustment takes into account not only how well does our model fit, but also how many variables or how many terms in our estimation did we include. The formula for this is 1 minus r squared multiplied by n minus 1 over n minus p minus 1. This r squared is going to be the r squared we found before. So that's this number. N is our number of observations. This p minus 1 accounts for all of the betas or all of the coefficients that we've estimated. The 1 is the intercept term, so beta naught. So p is the number of slope coefficients that we've calculated. Here, it's just beta 1. So this denominator is 4, which is our observation, minus 1 for beta 1, minus 1 for beta naught. So it will be 2. The numerator is just n minus 1. Our observations are 4. So the top part is just 4 minus 1, so it's 3. So if I were to write this right here, 1 minus 0.6695, I'm going to multiply this by 3 over 2. And this gives me approximately 0.5042. So our adjusted R squared, which takes into account how many coefficients did we estimate or did we use to get this model, is 0.5042. Our R squared that's not adjusted is 0.6695. The standard error then for our slope estimate is the next thing we're going to look at. And this has a somewhat, I don't know, it's not bad, formula. this is going to be the square root of the SSE over n minus p minus 1 divided by the sum of x minus x bar squared. Cool. So we have all of the pieces for this. It's just a matter of remembering what all do I put in here. Note, we take the square root of this because this stuff on the inside is effectively the variance of beta 1, or our estimate of beta 1. And since we want the standard error, like the standard deviation, we're going to take the square root of the variance. Cool. So I have all of the parts. My SSE is 568.18. N minus P minus 1, I found that before, and it's 2. This, we found, it's the denominator of our beta 1 coefficient. So we found this before, and for the data set we're using, it's 11. So I'm going to divide 568.8 by 2, and then by 11, and then I'm going to take the square root of the whole thing. Plugging these things in, this ends up being the square root of 25.826. And this is approximately 5.082. So we can use this standard error along with our point estimate of beta 1 is equal to 10.2273 to do hypothesis testing and confidence intervals. That's what we're going to look at now. So hypothesis testing, when we're doing regression, we typically focus on the hypothesis test where the null hypothesis is the coefficient that I'm looking at is 0. The alternative hypothesis then is that it's not equal to 0. If you remember back when we were doing hypothesis testing with sampling distributions of sample averages, we would find a t-stat where t is equal to the x bar we calculated, subtracted from, and then we would subtract off whatever we're looking at here and divide it by the standard error. Well, it's the same general setup, except we insert our value of beta 1 hat there, and we're testing against 0, so this is just 0. This means our t-stat is going to be our estimate of beta 1 divided by the standard error that we calculated for beta 1. For us, this is 10.2273 over 5.082, and this gives me a t-stat of 2.0124. The test we're doing is a t-test, and we're going to find some value t star from the t-table. We're going to go to the t-table, we're going to use our degrees of freedom that are equal to n minus p minus 1. Here, this is 2. And we'll conduct this at the 90% level. So we'll say 90% significance level, which gives me a t star that is 2.920. With this information, I can do my hypothesis test in the exact same way we were doing hypothesis testing from before, and I say Here is 2.920. Here is negative 2.920. Where does this value, so this is plus and minus, where does this value, or how does this compare to 2.920? If we're far enough away, we're able to reject the null. If we're not far enough away, we're unable to reject the null. Well, 2.0124 is somewhere like right here. So we are not far enough away to reject the null hypothesis. So we would say we fail to reject the null. Cool. That's hypothesis testing. It is virtually identical to the hypothesis testing we did when we had sampling standard deviation, sampling averages, and we're saying, how does this average compare to some hypothesis from before? Now we're just doing it with beta coefficients and their standard errors. The concepts, though, are the same. I take this difference between beta 1 and 0, I divide by the standard error, that gives me a t-stat. I then say, is that far enough away from 0? If it's far enough away, we reject the null. If it's not far enough away, we fail to reject the null. The last thing for this is confidence intervals. And confidence intervals, again, are the same setup from when we were doing them with sample averages. We are going to build a confidence interval that is equal to our point estimate of beta 1 plus and minus some margin of error. Our margin of error is built in the exact same way, where it's some t star multiplied by the standard error that we calculated. If I use the same 2 degrees of freedom and 90% significance level, I can use the same t star and say this is 2.920. My standard error is 5.082. So if I multiply these two things together, I get 14.839. So that's my margin of error. And then if I want to build my confidence interval, I can just add and subtract this from my point estimate and say 10.2273 plus and minus 14.839. And this is my 90% confidence interval for this setup.